We started off talking about waves, and then we started talking about light, and I recently said that light was, in fact, an electromagnetic wave. But how do we know that? How did people first learn that light was a wave? People guessed, but how did they know? Well, it turns out there's one really clear experiment that showed that light was definitely a wave, because light could do something that only waves can do, and that is something called interference. If you have a wave traveling along and you have another wave traveling along, we know that they can add together. That's how you get standing waves. If you have one wave doing this and another wave doing exactly the same thing, then they add together and you get a bigger wave. That's called constructive interference because both of the waves are what's called in phase. If they're going against each other, then they're out of phase and you get destructive interference, and so you get a very small wave. And what we've got here is a wave tank that can show you what happens when you have waves doing that. It's a water tank. It has two features. The first is it can provide you with unexpected sudden delivery of water onto expensive video equipment. And the other thing it can do is it can shine light through water where you're making waves, and so you can see a very clear picture of the interference pattern that you get. So what we have here is a pool of water. We've got a red bobbly thing going up and down inside the water. And so what that's doing is it's causing waves to spread out from that bobbly thing, and you can see them projected with the light just as shadows on the paper down here. And so the regions of high and low water act exactly like the lenses we talked about last time, and so they bend the light, and that's what gives us these lovely clear shadows down below. We can change the frequency of the wave by changing the frequency at which the bobbly thing goes up and down the water, and because the speed of the wave doesn't change, that means the wavelength has to get short. Because of the limited frame rate of the camera, it's kind of hard to see that when there's traveling waves, but you can see in the top right hand corner there's a standing wave where the wave is being reflected from the edge, and there you can see that the wavelength has got shorter. So what happens if I add a second red bobbly thing to our machine here? And then I'm going to have two sources of waves in my water. And so both of those waves are going to be spreading out from different points. If they're spreading out from different points, then we're going to have two waves coming together. Let's see what that does. So what we see is the two waves add together to give constructive and destructive interference in a pattern. And this pattern is called an interference pattern, as the two waves interfere with each other. And if you look extremely carefully, you can see there are some parts of this wave surface that are going up and down, and some parts where the water is actually still. And what that means is there are places where you always get destructive interference, and there are places where you always get constructive interference. That's easy to explain if we go to a diagram. So remember, you get interference when waves add up. And if waves add up in phase, like this, then you get a big wave, that's constructive interference. And if they add up out of phase, like this, then you get nothing, that's destructive interference. Now if you have two sources of waves, for example like the two red bubbles in a water tank, and they're both giving out waves of the same frequency, then those waves are going to meet, and depending on where they meet, they're going to be either in phase or out of phase. So imagine at the sources, they're going up and down at the same time, so they start off with the waves in phase. However, of course, they're going to go different distances, and if one travels one distance, and the other one travels a different distance, then they might go either in phase or out of phase. So the distance, the extra distance that one has to go, supposing they're in phase at one point, this is how far it has to go out of phase. It has to go from there over to here. Now how far is that? We've taken this point here from over this point to over that point. And so what is that distance? Well, this distance here from peak to peak is a wavelength. And so this distance here must be half that. So this is half a wavelength. So whether or not you get constructive or destructive interference depends on how much further one wave travels compared to the other. So if you have a wave traveling from one source to a point, and then you look at how far the wave has to go from the other source to get to the same point, this point is where they're going to add up, and so we're either going to get constructive, destructive interference or something in between. And that depends on what's called the path difference, the difference in how far the two waves have to go to get there. So this distance here, if that's an odd number of half wavelengths, then they're going to be out of phase and you're going to get destructive interference. If that's an even number of half wavelengths, they're going to be back in phase and then going to have constructive interference. So if we look around this area, we'll find all sorts of different points, and if we draw the distance that the wave has to go from each source to get to each different point, then at each of these points we're going to get different path length differences, so we get different constructive and destructive interference, and then what we get is a big interference pattern. So for waterways where you have destructive interference, you'll have points in that interference pattern where you have waves coming in but there's no actual movement of the water. If you have sound, then you'll have sound coming from two speakers and it'll exactly cancel, and so you'll have a quiet area. And you can only actually get this effect when the thing that's traveling is actually a wave. Destructive interference requires it to be a wave. If I was throwing actual particles together, then you'd always just get lots of particles where they meet. It doesn't matter whether they're in or out of phase, that doesn't mean anything. And so to test whether light is a wave, what people did was they tried to see whether it would make an interference pattern. And Young did this in the 1800s, and it turned out in order to get a nice interference pattern, he had to get the two sources really close together so that they were more or less only a wavelength or two apart. And since the wavelength of light that we see is around about a micron or a millionth of a meter, that meant Young had to get two very close slits together. And when he put the slits together, he saw regions of bright and dark light cast off from that, so he could tell, yes, I have an interference pattern, and therefore light is a wave. It took a few years for this idea that light was a wave to catch on. Thomas Young only published his double slit experiment in 1807, and a decade later the French Academy of Sciences was still unsure, and they launched a competition to explain the properties of light. Augustin Jean Fresnel put forth the theory that light was a wave, but one of the judges on the competition, Poisson, said that that was impossible because of the following idea. If you had a point source of light and you put a blockage in the way that was even, like a sphere, then every way that light would go round that sphere, if the wave went round the other side, then that would add up constructively because they'd go the same distance. And so all the ways that light could go round here would all be adding up constructively. And so if a light were a wave, what you should see is a bright spot in the middle of shadows. And he said, well, obviously there aren't bright spots in the middle of shadows, therefore the wave theory of light is wrong. Fortunately for science, the chair of the judging panel, Arago, thought to actually do the experiment. Now, to do the experiment, you have to make sure that the waves going on either side of the sphere go the same distance. And that means you have to make it smooth on the scale of the wavelength of light. And given that the wavelength of light is a micron, that meant he had to go to a lot of effort to make a blockage that was really, really smooth. And when he did that, what he saw was a bright spot in the middle of the shadow. So Fresnel and Young suggested that light were a wave. Arago actually proved that was true by showing there was a spot in the middle, and then that spot is often called Poisson Spot. Even though Poisson was using it as an example of something that was obviously absurd and wouldn't exist, and therefore light wasn't a wave.